This begins our new chapter on aqueous ionic equilibrium. So far in our journey, we talked about different styles of equilibrium, different ways to calculate, starting out with a Kc using molarity units, products over reactants where the coefficients become the powers, Kc for the concentrations in molarity. We talked about Kp, the equilibrium expression if we're using pressures for gases only. Kp for pressure. We introduced Ka, an equilibrium expression for weak acids. We also talked about Kb, an equilibrium expression for weak bases. The equilibrium arrow can also be applied to ionic compounds dissolved in water, typically called salts. We'll introduce a solubility product for ionic compounds, Ksp. Another approach to equilibrium studying a different category of aqueous solutions started with molarity, atmospheres of pressure, acids with pH values, bases with pOH values, and now a Ksp. So the journey continues. The term buffer is used to describe solutions that resist the changes in pH when an acid or base is added. Perhaps you've heard of buffered aspirin. Aspirin, of course, is an acid. Acetylsalicylic acid is the name of it. When we take acid into our stomach, which also is in an acid environment, it sometimes may lead to an upset stomach. So oftentimes we'll buffer that tablet. There's a brand name called buffered aspirin. What they do is add a chemical that coats that aspirin tablet to help the stomach digest that without upsetting it. And it does so by neutralizing excess acid or base that's done in a buffered solution. Just like everything else, there's a limit to what they can do, and eventually the pH may shift. Many buffers are mixed by taking a solution of a weak acid with a solution of its soluble salt. So for instance, blood is buffered by a mixture of carbonic acid and the hydrogen carbonate ion. For instance, carbonic acid is a weak acid, H2CO3. A salt that contains the same last name could be something like sodium hydrogen carbonate. We commonly call that baking soda. So this negative ion, it does have to have a first name. I just picked sodium, perhaps potassium, lithium, any first family metal. Sodium bicarbonate is most commonly called baking soda and used readily every day. So a buffered solution is made by taking a weak acid and a solution of its soluble salt. An acid with its salt creates a buffered solution. So if I take a weak acid in this visual and a conjugate base, now conjugates come from the Bronsted-Lowry Theory. Conjugate base only differ by a hydrogen ion. Think about what we just wrote, H2CO3, carbonic acid, and its conjugate base, the bicarbonate ion. These two are conjugate pairs that when poured together, let me draw that better. H2CO3 is the acid, the conjugate base is the bicarbonate ion. Perhaps this is baking soda dissolved in water, sodium bicarbonate. We pour those into the same solution to create a buffer. So we have all kinds of opportunities for buffers. From the previous slide, carbonic acid with hydrogen carbonate. Perhaps we take a weak acid like acetic acid, vinegar, and its conjugate base, acetate ion. Give it a first name such as sodium and we come up with a salt, sodium acetate. In solution, we can take a weak acid and a salt that has the same last name, a conjugate base, to create a buffer. In solution, we would have molecular acid, its conjugate base acetate. We'd have the hydronium ion and the sodium ion then also produced as spectators. So buffered solutions are solutions that are there to help resist a change in pH. Let's suppose then we have a weak acid. We'll just call that HA. And I place that into water and we see a proton transfer. The proton transfer says HA and A negative. And this A just stands for any last name, the anion on a weak acid. The anion, A negative. These two are conjugate pairs. I would label this the acid and this its conjugate base. Water then must be acting as a base and its conjugate acid, hydronium. So the Bronsted-Lowry theory. The buffer works by an application of Le Chatelier's principle. Buffer solutions contain significant amounts of the weak acid and equal amounts of the conjugate base. So thinking about Le Chatelier, suppose into this solution that contains HA and A negative, an acid and its conjugate base. Think through Le Chatelier. Let's suppose we add base. If we add base to the solution, a couple of things might happen. Adding base neutralizes the acid. Adding a base to an acid neutralizes that to make another water molecule. You can think of it as hydronium combining with hydroxide to make a water. A proton has been transferred. The hydronium is then replaced by the shifting equilibrium. Taking a look at Le Chatelier, trying to understand if HA is being consumed by adding OH negative, we're going to make more of the conjugate base A negative and water as the driving force of that neutralization reaction. Acid plus base will neutralize to make a water. So, thinking about a buffered solution, if I add a base to an acid, I neutralize and create more of its conjugate base. Think of it this way, and this is a dark picture, hopefully yours is showing up. I've added hydroxide into an equilibrium. Adding hydroxide, here's the equilibrium arrow. The hydroxide ion going to react with HA. In this box says HA. You're going to produce more A negative and hydronium, adding the water up at the top as the byproduct. Buffers work in conjugate pairs.